Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the adiabatic process. So adiabatic process is the process in which the heat exchange is zero, which means that there is no heat exchange between the surroundings and the system. Okay, so we can say that if dq is 0, then 0 will be equal to du plus dw, and dw will be equal to minus of du, which means that if dw is positive, which means that in expansion of the gas, du will be negative, which means temperature falls, and vice versa, which means that if dw is negative, then this is compression, and in this case du will be positive, temperature increases. Let me tell you the condition for this. You can see that the walls of the container are non-conducting, which means that system cannot exchange any amount of heat with the surroundings. So this would be a adiabatic process. Now if I compress the gas, if I push down this piston, then the gas molecules will come nearby to each other, and they will collide more and more, and therefore more amount of heat would be generated, which could not be disposed of from the system to the surroundings due to the presence of adiabatic walls, which is non-conducting walls, and hence the temperature will increase due to that extra amount of heat generated. Or if I pull up this piston, if I expand the gas, then the molecules will separate apart and their collisions will decrease, and there would be a deficiency of heat, and therefore the temperature will decrease, because that deficiency could not be fulfilled by the atmosphere, as the system has non-conducting walls. Okay, so this is the first thing. So if in adiabatic process, if the work done of the gas is positive, which means in expansion the temperature of the gas will decrease, and if the work done by the gas is negative, which means in compression, the temperature of the gas will increase. Now let us derive the expression for the process adiabatic. So we know that 0 will be equal to du plus dw, and dw is the work done, which is p dv. Okay, obviously p is variable, I know that, but in any process work done can be written as p dv. If p is variable, then we have to put the p in terms of volume, and we have to integrate this term. But in this case, p dv, p is also variable obviously. Now you know that du is equal to n cv dt. Okay, so this is du, and we also know that du is equal to n cv is r upon gamma minus 1 into dt, and p dv, pv is equal to nRT, and by differentiating this equation we can say that p dv plus v dp is equal to nr dt. So if we substitute the value of nr dt here, then du will be equal to 1 upon gamma minus 1 into p dv plus v dp. This is du. So now if we put the value of du in the first equation, in this equation here, then let us use the next page. So P dV plus V dP upon gamma minus 1 plus dW. dW was already P dV, so plus P dV will be equal to 0, and therefore we can say that P dV 1 plus 1 upon gamma minus 1 will be equal to minus of V dP divided by gamma minus 1. So this is P dV into gamma, that is equal to minus of V dP, and therefore P, in fact we can write down it as dV upon V into gamma plus dP upon P is equal to 0. And if we integrate these terms, then it would be ln V into gamma plus ln P is equal to C, where the integration of 0 is C, because differentiation of C is 0. So this is ln PV to the power gamma is C. You know the property of log that this gamma can jump on the power of volume. So we can say that PV to the power gamma is constant, and this is the process equation of adiabatic process. So for adiabatic process, PV to the power gamma is the characteristic equation, and if we substitute the value of pressure as nRT by volume, then this is nRT by V into V to the power gamma is constant, and obviously R and N is constant, so we can also write it as TV to the power gamma minus 1 is constant. So this is also a form of adiabatic equation. And now we can also obviously eliminate the volume, and we can write the volume V as N as P upon nRT. So in P, V to the power gamma is equal to constant. Let us eliminate the volume. Volume can be written as nRT upon P. This is the volume. So P into nRT upon P to the power gamma is constant, and this is P to the power 1 minus gamma T to the power gamma. You can see that this is P, and in the denominator it would be P to the power gamma. So P to the power 1 minus gamma into T to the power gamma is equal to constant. So this is the equation of adiabatic process in another form. So now let us also find out, and now let us see that what is the graph of adiabatic process. So we know that P is inversely proportional to V to the power gamma, and therefore this relationship will again be a hyperbola, but not rectangular hyperbola obviously. And we know that gamma is obviously greater than 1 because Cp is greater than Cv. Therefore the slope of this graph would be greater than the slope of isothermal process. And interestingly, if I plot these three processes, first one is isobaric process. This would be the constant pressure. This is V initial and this is V final. And then I plot isothermal process. This is isobaric. This is isothermal. And if I plot the adiabatic process, so this is adiabatic process. So you can see that these three processes are as shown, and the minimum amount of work done would be in adiabatic process, because work done is represented by the area under the graph and volume axis. So this is the minimum area, and the maximum area is under the isobaric curve. So I can say that the work done in isobaric process is highest, then the work done in isothermal process and then the work done in adiabatic process. So this is the sequence of work done in these three processes. The highest work done is for adiabatic isobaric process, and the lowest work done is for adiabatic process. And this is obviously when the change in volume is same for all of these three processes. Now, why we have drawn this graph below the isothermal graph? It is due to the fact that if we find out the slope of this graph, so let us see the slope. So slope of this graph is dp by dv, and slope can be calculated by differentiating the PV equation. So we know that PV to the power gamma is constant, and if we differentiate this equation, dp into V to the power gamma plus gamma into V to the power gamma minus 1 into dV into P is equal to constant, is equal to 0. Okay, then you can see that dp by dv will be equal to minus of P by V into gamma. You can see that this is gamma P by V. Okay, so this is the slope of this adiabatic curve, and we know that the slope of isothermal curve was minus of P by V. So this slope and gamma is obviously greater than 1. So the magnitude of slope dp by dv, magnitude for adiabatic process, is equal to gamma times of dp by dv magnitude for isothermal process. Okay, and gamma is obviously greater than 1. So if we draw the two graph for the same initial and final volume, then we will see that the graph which has the more slope will be below the first graph. So this curve would be adiabatic, this is adiabatic process, and this is isothermal process. Okay, now if we talk about the bulk modulus, then bulk modulus is minus dp by dv by v, and as we know that it is gamma p. So bulk modulus is this, and compressibility will be 1 upon bulk modulus, and therefore it would be equal to 1 upon gamma p. Okay, and if we find out the specific heat for adiabatic process, C is 0 because C is equal to Q by M delta T, and obviously Q is 0, so therefore C is 0. Okay, we cannot exchange any heat to raise or to decrease the temperature of the gas in adiabatic process. Now if we check the work done in adiabatic process, so work done, again we write it down as P dV, and now we know that P1, or we can say that P is equal to some constant upon V to the power gamma. So work done will be equal to C upon V to the power gamma dV, integration, limit would be from V1 to V2, and this would be equal to C is common, and integration of 1 upon V to the power gamma will be V to the power 1 minus gamma upon 1 minus gamma. Okay, and the limit would be from V1 to V2. So work done will be equal to C upon 1 minus gamma, and this would be V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Now let us multiply this C with both these terms. So this is 1 upon 1 minus gamma, and this is C V2 to to the power 1 minus gamma minus C V1 to the power 1 minus gamma. And we know that P1 V1 to the power gamma is equal to P2 V to the power gamma, and that is equal to C. And now let us substitute the value of C in these two terms. But we know that if we are substituting the value of C in this one, we have to substitute V2, this term, and if we are substituting the value of C in this term, then we have to substitute this term. So let us substitute accordingly. So this is 1 upon gamma 1 minus gamma. It is C. C will be P2 V2 to the power gamma into V to the power 1 minus gamma minus C is P1 V1 to the power gamma into V1 to the power 1 minus gamma. Okay, so if we cancel out V to the power gamma, so work done will be 1 upon 1 minus gamma, and this is P2 V2 minus P1 V1. Okay, so this is one expression of work done, and we can also say that P1 V1 will be equal to NR T1 and P2 V2 will be equal to NR T2. So work done will be equal to NR upon 1 minus gamma and multiplied by T2 minus T1. So this is the work done in adiabatic process. Now let us see that what are the necessary conditions for adiabatic process. So the necessary conditions for adiabatic process can be easily obtained by thinking about a piston enclosing a gas in a cylinder. So we have already discussed that if we need to stop any exchange of heat of the gas with the surroundings, the walls of the container should be non-conducting walls. So the first and foremost important condition is the walls of the system should be non-conducting. Okay, and the second thing, if by chance if we see that this system has a conducting walls by some extent, if we are not able to provide the non-conducting walls, then what should we do to use this system as an adiabatic process? So what we will do, we will suddenly compress the gas or we will suddenly expand the gas. And this is very important due to the fact that if we suddenly compress or suddenly expand this gas, then what will happen, that gas will have no time to exchange the heat with the surroundings. Therefore the process will be adiabatic process. So to provide no time to gas to exchange the heat with surroundings, the process should occur suddenly at a higher pace. So this is the adiabatic process, and let us also discuss the gamma for adiabatic process. That gamma was the volumetric expansion coefficient. It was dV by V dt. Now we know that T V to the power gamma minus 1 is constant. This is also the adiabatic equation. So if we differentiate this equation, then dt into v to the power gamma minus 1 plus gamma minus 1 into v to the power gamma minus 2 into dv into t is 0. So this is the differentiation of this term, and we need to find out the dv upon we know that gamma will be equal to dv upon v dt. So we need to find out dv upon v dt. So dt into v to the power gamma minus 1 into, that is equal to minus of t into dv into gamma minus 1 into v to the power gamma minus 1 upon v. What I have done, I have written v to the power gamma minus 2 as this term. So you can see that we can cancel out v to the power gamma minus 1, and if we wish to find out dv upon v dt, then dv upon v dt will be equal to minus of 1 upon t into gamma minus 1. So this would be the gamma for this process. Okay, so this is the complete analysis of this adiabatic process, and in the next video I'll be bringing the complete detailed analysis of polytropic process. Thank you.